It is my pleasure to introduce Ken Lanier from Teradyne, who will be talking about optimizing tests based on device temperature. Ken has been in the ATE industry for a long time. He's held positions in application engineering, system instrument design, as well as engineering and marketing management. He is currently principal technologist in the SoC test division at Teradyne. He is in Massachusetts, where it's currently snowing. Previously, he was a director of marketing at LTX, and he has a bachelor's degree in electrical engineering from Worcester Polytechnic Institute. So it is my great pleasure to welcome Ken.
Thank you, Ira. And welcome to everybody. I know a lot of people in different time zones, so whatever time of day it is for you, welcome. What I want to do here is a couple things. First, I want to talk about this problem of too hot to test from a holistic point of view. Teradyne, as you're probably aware, is an equipment supplier, but testers don't live in a vacuum. We interface to a lot of different software and hardware tools, and those connections are what allow us to help solve this problem. And every great problem that you want to solve, you want to have a success metric. And I think the one that it always comes down to is cost. So we want to use that as a metric in terms of determining how well we're doing. There's a lot of different work being discussed in the slides here with a couple different partners. The work is in various stages of completion, but all of the technology exists and the work to integrate it is ongoing. So with that, I think everybody's talked about the problem, so I'm not going to spend a whole ton of time with that. But the device does heat up, but we want to do more and more tests at wafer probe, and if we do that, there's no package to conduct away heat, as was discussed earlier, and also the ability to have any cooling or much less control at probe is very difficult. A lot of discussion about packages. I like the keynote address. There was a lot of criteria to describe what kind of package you will choose. Test was not among them, though you might have noticed. So these large sort of exotic packages are very difficult to handle automatically and take advantage of any of the heat management capability in those packages. And then, as was discussed previously, device behavior changes with the thermal characteristics of the device. And the major problem, as I said before, is this costs money. Nobody likes wasting money. So there's sort of a minor problem here. To manage a lot of these thermal effects, test time can go up, meaning more equipment time is required. So that costs some money. The major problem, though, is that thermal issues, as was discussed, they cause the device to behave differently. And because nobody likes shipping bad devices, the most likely outcome is device overkill, throwing away good devices. Nobody and people really don't like doing that. We have some crude solutions today. We can monitor package temperatures to control thermal control systems inside handlers, or we can slow down testing until we reach our goals in terms of performance of the device. That was discussed previously as well. A lot of talk about die temperature sensing. As an equipment manufacturer who has to deal with a lot of different designs from a lot of different places, you can monitor die temperature, but trying to do it during production tests is really not practical. There's really no consistency in terms of how this is implemented, whether it's an analog thing, a digital thing, how you read it back, how much circuitry you have to have on the test hardware in order to do current to voltage conversions, whatever it is that you have to do. So die temperature monitors, practically speaking, don't really help us in test. And I said we'd use cost as a metric, and just a few comments about cost of test. This is sort of an area of, that I talk about a lot in IEEE committees and with customers. Some fun facts here. Yield is everything. I think everybody knows that. If customers could increase their yield, especially for these large monolithic devices, by 2 to 3%, they would make a whole lot more money. depending on what you're doing, what your silicon costs are, if you could increase yield somewhere between 1% and 2%, test is free, just to put things in perspective. Test really isn't that expensive relative to other things that can go wrong. If you look at test time, we spend a lot of time fixing devices, not testing them. So if you look at time to do repair, harvesting, trim, things like that, they can consume anywhere 30, 40, 50% of the test time, depending on the nature of the device. These large heterogeneous integration devices tend to have a lot more of this going on. And it takes a long time to generate a test program. Arun talked about this a little bit in his setup. I happen to like this graphic in terms of, how much work goes into making these devices. So if you extrapolate to 5 nanometers, it's like you're building the Empire State Building every time you're doing a device. And if you look at the amount of effort going up, you look at the budget for test engineering, and a lot of times it really doesn't keep up with the rest of the development budget. And so what happens is at the very end of the development cycle, test is the last thing that happens. So it's naturally a very compressed process because as soon as test is done, you can start shipping devices. And if you're behind anyways, that just puts more pressure on it. So test engineers have to generate test programs just as a metric, can have hundreds of thousands of lines of code, millions of lines of pattern, and each one of them must work perfectly or you start having test escape. So this is sort of the backdrop of that cost of test question that I was discussing earlier. Again, everybody understands scan test, I think. It's built to toggle a lot of transistors. It is a very unnatural state for the device. As such, and again, as Arun demonstrated, it consumes a lot more power, generates a lot more heat than it ever will in mission mode. So again, the packaging is never built to deal with this problem, which only complicates the test situation. And if you wanted, from a cost point of view, you want to do as much test as possible at probe. And again, probe, it makes this even more difficult. There is no package, and any kind of temperature control is much more complicated and than it is at package. So again, this just makes the problem harder and harder. And again, it's only during test. Again, a long discussion of what package technology you'd pick, things like that. Test needs typically never enter the conversation. What we can do today. So we can slow down the shift rates. That increases test time. Arun talked about that. We can look at test order, go back and try different orders of tests. We can try, spreading out the heat a little bit by doing patterns that exercise different portions of the device. That takes a long time. That's a very iterative process, and it delays time to market, which is another huge cost. Again, getting to market late makes all the other can make all the other questions moot. Because if you're not to market in time, you don't sell any parts. And the other thing is we can add a lot of automatic temperature control to both IC handlers and prober chucks. It's expensive, and as Arun discussed, it's fairly imprecise the way it works now. So some things going on. So a couple slides from our friends at Siemens. So historically, there's things that people have done to try and manage the heat in the device. So some of these things Arun talked about, moving around shift clocks, moving around patterns. You can take and try and isolate certain parts of the device, do some more work on the device, toggle some more transistors. Down the bottom, as I said, you can start to try and spread out the patterns based on the physical layout of the device to try and make the heat get the hotspots distributed across the device a little bit better. So recently, as discussed at ITC this past year, one of the interesting innovations is a streaming scan network. And basically what happens is there's a stream of data going through the device, and various IP blocks pick data off the stream, under some sort of programmable conditions. Now, what's interesting about this, a couple things, it tends to shorten scan chains. So if you look at the number of overall cycles required to do the same amount of testing, in this case, the case cited in the ITC paper, it's about a 40% reduction in overall test cycles, which is great because remember, cycles generate heat, and we're fewer cycles, the less heat. The other thing that's kind of interesting about this is historically, when we do scan tests on the device, we don't get to manipulate a lot of what's going on with the scan except externally to the device. So we can change scan clock rates, we can change scan data, but generally what happens at the IO pin on the device very closely mirrors what's going on in the IP block that you're trying to test. And the benefit here is that there's now what's going on external to the device is disconnected from what's going on internally, because now you can program how much data these IP blocks are taking off the bus, how fast they're taking it off, things like that. So there's a lot of knobs here that sort of disconnect what's going on at the outside of the device from what's going on the inside. So there's a lot of adjustability here that you can take advantage of as well. So that's gives us a glimmer of hope that we have a little bit more control about what's going on in the device. We've talked about active thermal control systems. So, it's a fairly simple concept. There's a liquid cooling system inside the handler or prober. It works like a lot of cooling systems in that the water is always heated through some sort of laser heating system or some other system you can turn on and off quickly. And so it's not a matter that you're cooling down the liquid going through the system, as you're heating it up more or less depending where you are and how you're controlling this. Now, you have to, there's a couple of ways that you can control this system, right? You'd like the system to be dynamic. You'd like it to be adaptive. The simple one is you can monitor the package temperature. This is really easy to do. There's a temperature sensor in the chuck. It's all self-contained in the handler. The problem, of course, as was noted earlier, if there's a lot of thermal mass going on, and it's really a lagging indicator of what's going on, and you can really only measure one thing, which is the package. The other thing you can do is a die temperature readback. It is exactly what you care about. You can measure multiple locations. The problem is as I said before, there's no uniformity in implementing this thing. And the latency, by the time you get data back from the device, you process it, make some decisions, and send instructions to the temperature control system, it's pretty much too late. The other thing, which is actually sort of a mix between, kind of splits the difference between the two, is monitoring device power supplies. So again, this is kind of it is an early indicator of temperature, but there's not a direct, it's not a perfect correlation between power supply and what's going on in the device temperature. You can get core specific information because they're typically different power supplies per core. Again, the only drawback here is you do have another latency problem. By the time that you can monitor this pretty quickly, but by the time you get information to the ATC system decides what to do about it, goes through its own, has its own thermal delay. Again, it's a little late for what you need. So the problem basically for a lot of these is that while they are adaptive, they're not predictive. So you always find out after the fact, one way or the other. So if you're trying to control the ATC system and you're trying to do it by one of these three things, none of those three techniques is perfect. And
so Ken, a question,
sure.
how long of a delay are we talking? Are we talking milliseconds, seconds? I mean, by the time, well, there's both the time for the control system to figure it out, and there's a certain amount of time to change the actual temperature of the thermal mass, right? I mean,
that's correct. I think there's a gentleman from Cohu presenting on Friday. He probably has some better data, but I mean, it's at least tens of milliseconds for the ATC system to do its thing, just thermally. But again, the ATC system has to make some decisions, so there's a little bit of processing that goes on there. And again, if you're monitoring package or die temperature, all these are lagging indicators. So you're getting late information to the ATC system to start with. So regardless if the ATC system was instantaneous, more often than not, you still won't get it, information in time.
Thank you.
All right, so we've decided that none of this is perfect. So if you'd like to get a little closer to perfection, so if you'd like it to be easy, you'd like it to be exactly what you care about, you'd like it to be an early indicator, you need to solve the fact that you only have lagging indicators, there's no uniformity in getting performance data back from the device, and the fact that it's not predictive. And again, this is where some new technology starts to help us out. One of the companies that's doing a lot with this is a company called Protientex. But this is an example of the kind of thing you'd need to do in a device design to start making this work. Now, the problem that Protientex is trying to solve is much larger than just thermal control during tests. So, they're looking at correlating test data to designs, what's going on in design, going on to life testing of the device, built-in test the thing is out in its final application. But, if you look at sort of the sliver of it that we care about, in this discussion, it's exactly what you care about. You can monitor die temperature and you can put as many sensors on as you care to. The beauty of it is there is a controller on board, and that controller gives you a universal interface to the outside world, which is what we do not have now, and is one of the biggest impediments to using any sort of die sensing technology, is that if you go from IC vendor to IC vendor, EDA provider to EDA provider, nobody standardizes any of these interfaces. So it's sort of useless to anyone who's trying to use them. And this, the fact that you can have an IP provider standardize this interface is sort of a huge leap forward for us. The other thing is that it's exactly what you want, and it's extensible. You can extend it to monitor different things on the device, but for the purposes of this discussion, at least you get a good readback of what's going on in the device with some granularity without doing a whole ton of work. And that's sort of what we're after. So you get these various components that you can now put together. And so, again, if you think, I said no tester exists in a vacuum, but the tester tends to be sort of the center of the world, because everything attaches to it. So, what can the tester do? Number one, it can monitor what's going on in the device. The tester has loads of characterization tools. So, you can load up, tons and tons of, I want to run, 1,000 different shmoo plots varying a whole ton of different things. You can queue all those up, go home, come back the next morning, and the tester will have done all that work for you. So that's what the tester can do. It's very good at data collection, raw data collection, doing it algorithmically, doing it, and being able to collect just loads and loads and loads and loads of data. Nobody ever accused testers of not collecting enough data. The problem typically is, what do you do with all of it? So what you can do with this data, number one, you can feed back to the design process pretty easily. You can go back, you can say, well, this part of the device got hot when you were running this pattern. So this gets to Arun's point about, for both scan and BIS testing, you can now go back and correlate specific locations on the die that got hot when you were doing specific operations based on different patterns. So you can go back and do a little better correlation of what's going on the device, and as you're running a specific pattern, feedback to the design and ATPG processes, and make some adjustments either in the design, in the patterns, the order in which the patterns are run, so on and so on.
So, but Ken, is that an automated process today, or is that still a manual where the test engineer has to sit down with a chip designer?
A test engineer sitting down with a chip designer would be a great accomplishment. The But it is not an automated process right now. I mean, just doing scan fail captures right now to get just scan fail information back into a design flow and getting patterns changed just to fix errors is an incredibly much longer process than it needs to be. So I'm going to talk about that in a couple slides, in terms of, a lot of our problems here aren't technical, they're cultural.
Understood.
Okay. Sorry. So the other thing you can do is, the tester collects loads and loads of data. Right now you can export all that data. I mean, that's what happens with a lot of the sensor information right now. There's just loads and loads of data log information that gets analyzed offline. You can actually move some of that machine learning on into the tester. Testers can host additional computers that can do this stuff, either in real time while you're doing production, but more likely, you would use the results of the machine learning to do something like altering the test program flow. You can either do that sort of in real time, while you're doing production, or again, you can sort of take the learning and sort of the next lot you load, you can use the results of that learning to alter the flow of the test program. The other thing you can do with this that's sort of intriguing too is, when you're talking to the ATC system, if you know what's going to happen on the device when you run a certain pattern or a certain sequence of patterns, now you can potentially get into the realm of predictive control, right? So the means by which testers control ATC systems is there's one of two ways to do that. You can do it through a digital interface, or you can send analog control signals from the tester back into the ATC system. And in both cases, the tester would have the capability to send information to the ATC system before it was needed. So getting back to your point, what's the lag? If you can get information there before you start the pattern, you can actually get the ATC system to do something in time to do some good. So again, all this technology exists. And again, we are, the work we're doing is in various stages of development to implement it. But if you look, there's a few technical challenges. The first is that test programs are phenomenally complex, and the flow through those test programs tends to vary. So depending on if you're doing device harvesting, device grading, retest, trim, repair, whatever, a lot of this depends on the test flow being consistent from device to device to device, or at the very least, not having a lot of variations to it. So within one device, from run to run, the pattern flow can change. If you get into a multi-site situation, you can have two sites doing two different things. So again, that makes the problem multidimensional, both for the control and the ATC system. And again, all this makes predictive modeling more difficult because again, any variations in the test flow or variations from site to site can make it more difficult to have a predictive model that's going to fit for the bulk of the test runs. So we said we'd use cost as a metric for all this, and this is where sort of the opportunities come in. So this is kind of a good news, bad news sort of thing, and I'm the kind of person who likes their bad news first. So we'll talk about that. So what may limit the gains, as I said before, the test flows could get too dynamic, and there's just too many permutations to deal with. Secondly, a lot of devices that we're seeing, especially more heterogeneous type of devices, scans becoming a smaller and smaller portion of the overall test time. Now, as Arun said, there's BIS tests that generate a lot of heat, but scan tests are usually the worst offenders. And if they become a smaller portion of the overall test time, the throughput gains that you get may be limited. And more, to the point, all the work involved here, this gets back to your question, Ira, is what do you do with this data, right? The work to collect the data, collecting the data is not that hard. The work to change the test flow, well, that's not too hard because we do things like that with tools like Optimal Plus, which, we change test flows based on test results. Predictive control of ATC systems, it's not been done, but theoretically, it's not too hard for the tester to do once you kind of know what you want to do. Feeding back data to the design world and getting them to do something with it historically has been the most challenging part of any of this. Again, I mean, we struggle now with just feeding back simple things like, well, the scan test failed on this cycle. Could you send me a new pattern? Right, the turnaround time to do something like that tends to be pretty long. So you can imagine well, here's the heat signature I got. Could you, work on the design or the patterns to alleviate that? That's a much more complex communication flow, and that's probably one of the biggest impediments is getting that loop to be much tighter than it is. But the opportunities are enticing. If you can get faster test times, that's great. That lowers cost of tests specifically. So that's a win. If you can get better yields because the die temperature is better controlled, or you have to do less retesting, again, better yields trump everything. A couple percent more yield because you controlled the temperature of the device better represents a phenomenal amount of money, especially on these newer process nodes. You can optimize test flows again to get either faster test times or better yield. And then this, we're talking about temperature today, but if you can monitor voltage drops on the die, you can monitor the accuracy of reference voltages, things like that. You can extend the same concept to solve other problems. Voltage drops on the die are, problem number 1 or 2, fights with the thermal one, so being able to address a problem like that by more accurately monitoring what's going on in the device and altering the test flow would be a big win as well. So anyways, that's what I had prepared. Happy to take questions, but I'd also like to thank the folks at Protientex and Siemens for contributing to this, both material and some very productive discussions. So I'd like to thank them and take any more questions if there are any.
So a question in terms of the Protientex, I mean, it's the number of sensors, just how much the die area you want to consume. I'm assuming they're small, but they have to be inserted and they take up real estate.
That's correct. So I think I think they could probably tell you in more detail exactly how much die area is taken up for different kinds of sensing. And actually the bigger die area is probably more the controller function, but even that's, relatively small, given the amount of die area we dedicate to scan circuitry, the amount of die area for this stuff is pretty small.
Understood, but it's obviously something that's got to be done back in the design. They got to decide they're using it and then put it in there. Great. I think that's about it on the open questions. I thank you very much, Ken. Want to once again thank our sponsors who made this event not only possible, but made it free for everybody to attend: Advantest, Amcor, Indium, Form Factor, and Nidec SVTCL. And Advantest, once again, is a global leader in the ATE industry with nanotechnology products supporting leading edge with a diverse workforce and eco-friendly policies. Amcor is driven in the areas of technology, quality, and service in terms of advanced packaging, high quality execution, and a complete array of services from design and test through drop ship with a manufacturing footprint throughout the world. And Indium, with premier assembly materials designer and manufacturer of thermal interface materials, solders, paste fluxes, and materials and compounds. So when you have an opportunity, please thank all of our sponsors and encourage them to help drive future events, but we're very thankful for their support of Too Hot to Test. And I will wish everybody a good rest of your day. Thank you for joining us.